Welcome everybody to ShockWeek and the ground fault circuit interrupter and shock. What we know about things like the 4 to 6 milliamp pickup levels we're going to be talking about today. We're going to be talking about some of the history behind that. We're going to be talking about the pickup levels from a European standard, from a not UL 943 standard. Nihad is very knowledgeable in that area, and that tells me that reminds me that I've got Nihad El Sharif with me today. He's a good friend of mine. He's a very smart individual. He and I wrote an IEEE paper together, and I would like to give Nihad a few seconds, or Nihad, just do your introduction. Let everybody know on YouTube who you are, and let them know what you do.
Oh, perfect. First of all, thank you for the compliment, Tom. I'm just learning from the best. And like you said, yeah, Tom and I are very good friends. We've known each other for about a few years now, and we just had our first paper, co-author paper together. We presented it in March. Luckily, it was the last week right before the lockdown. So electric safety workshop and IEEE conference in Reno. And I'm looking forward. Tom and I are working on another paper, so hopefully maybe soon we'll have another program on that paper on AFCIs. But yeah, I guess my name is Nihad El Sharif. My friends call me the sheriff. Sometimes I have a sheriff for my Texas conference I went to, like a sheriff badge. Like I said, I'm an electrical engineer, professional electrical engineer. I have a master's in engineering, electrical engineering, and an MBA. I started my career in R&D, research and development, and actually I was lucky that the project I worked on was designing a special purpose GFCI, like class C, D, and E, which is something Tom and I were going to be covering during this presentation. And then I moved into product management, marketing, business development, if you may, for a few years. Now I'm on my own, I have my company. I know the name might be hard to pronounce. It's Monkey Bar. So I just tried to be creative to put my MBA in action here. So I have my Monkey Bar, all capital letters, and I drop the vowels. Monkey Bar Technologies Inc. I'm based out of Saskatchewan, in Canada. And yeah, just working in different project consulting, whatsoever. So looking forward to this program, Tom.
Awesome. And I'm honored to have you here, Nihad, and thanks for helping me kick off Shock Week. And we are talking again about GFCI, the NEC, and from a standards perspective, I have my 70E book because we're going to be talking about 70E. I just had to grab it off my shelf. I also have the 2020 version of the National Electrical Code, and I go back to the 1940s in the National Electrical Code, which I don't have to worry about going back that far because I think I just have to go back to the early 70s, and we're going to talk about some of that history around GFCIs and the NEC in addition to the standards and whatnot. So,
for the invite, Tom, I appreciate it. It's an honor.
Awesome. So now, Nihad, you and I had talked about this before, and I know that we're going to talk. I'm going to be with Jim Dollard later on this week, I believe Thursday, talking about 70E as well. NFPA 70E in the Annex K. A lot of people, don't read the annexes. The annex material in 70E is just like annex material in the National Electrical Code. It's not enforceable. It's informational in nature, but the 2018 version of this book added a lot of really good information in Annex K around shock, and a couple key things that I pulled out of that annex that I wanted to share on this call was some of the statistics. They say 98% of fatal occupational electrical injuries are electrical shock injuries. So, what strikes me, Nihad, is that when we talk safety, we love to talk about the explosions and we talk about the arc flash events, but a lot of people don't realize that more people die from shock every year than things like arc flash events.
Yeah, I totally agree. I think, and I've seen this, I agree with you, Tom. It's probably because of how the explosion just gets a lot of attention.
Yeah.
It's very, I guess, what the word I'm thinking of, it's just very
dramatic,
disturbing, right? But shock can just go under the radar. Anyone can be shocked. I mean, I got shocked before working in R&D. I'm an engineer, like I said, and I didn't deal with any high voltage or anything. But I think all of us here on the call, I would say most of us had, at some point in time, got a little shock, a little zap. So it's just something that I guess we tend to not take seriously because it happens more often. But arc explosions or arc blast, arc flash is very serious, but it doesn't happen as often, Plus, we also spend I would say over the last 20, 25 years, there's been a lot of great things that have been done to address arc flash incidents, like 70E, all the PPE stuff, all the elimination, like the hierarchy of control. So there's a lot of great things that happened, and I believe it just helped the industry quite a bit.
Absolutely. And the other thing 70E tells us is that this exposure from a shock perspective is not just an impact to the electrical worker. We're in the electrical industry. As an engineer, myself and Nihad, we might be in a lab exposed to those shock hazards. But the electrical worker that's out in the field, it gets exposed to these all the time just because of their natural duties of work. They need to establish electrical safe work conditions, etc. And no matter what they do, they're always, since that's their business, they put themselves on that front line, and they understand the hazards, but they're the most exposed. But 70E and Annex K tells us that it's not just the electrical person, it's the non-electrical workers. And I would even, this is a workplace safety, because 70E focuses on the electrical standard for electrical safety in the workplace. But if you think about it from beyond anybody who's actually working, there's exposure to electricity just from everybody who operates in a building or a structure that is energized in and around electricity. There's exposure to non-workers as well, right? But this statement out of 70E Annex K reminds us that what we do as electrical professionals not only impacts the electrical professional, it also impacts other people on that job site, and even homeowners and people that have to live and occupy that structure that we're energizing.
Tom, I totally agree with you. Over the years at Electric Safety Workshop, you've been very heavily involved with the Electric Safety Workshop IEEE conference, and there are quite some papers that have been presented on electric shock for non-electrical workers. I had the honor of publishing or presenting a paper, I think it was 2017, just the impact on non-electrical workers. The craziest story that I ever had, when you think of it, and this was a good friend of mine told me this. It was a lady in an office setup. She's like, how would you get shock? And it's just like, she doesn't really deal with electricity. But apparently she was wearing a bracelet with some like metal, like little things coming off the bracelet. And she was reaching over to plug something into a power bar. And somehow those metal things went into the power bar and made contact. And she had a burn around her arm. Wow. or rest. So it's kind of crazy. I don't never think of this, but weird things happen. It's
Absolutely.
Just an office person.
Absolutely. And electricity is all around us. And we don't, a lot of people, we talk about ground fault circuit interrupters as that last level of defense. We don't need that unless something goes wrong, right? We don't set out the morning to come in contact with some energized part. That usually occurs as a mistake. Something went wrong in that whole process. And what's interesting about our industry is, electricity, when we first got electricity, and you had the George Westinghouse days and the Edison days and all of that, and they're bringing electricity into the homes or into our place of businesses, right? So back in the day when electricity was first introduced to our markets, they used it heavily for manufacturing facilities where they were making things. Where they would typically use steam-driven tools and whatnot. That leaned more towards electrical type of products for motors and etc. So when we think about shock, and you think about back in the day, we all know how safety probably did not get a very good focus back in the day, right? So that didn't mean they didn't see any shocks. It just meant that they didn't know how to handle it. So there was a lot of research done, and I happened upon a study from the 30s that was conducted. It was a UL study, and in my humble opinion, based upon my research, Nihad, I look at it and say a lot of what we learned started back in the late 20s and early 30s, And it focused, the studies focused around solutions in the farm and the agriculture world, because what was going on back then was you had this new, you had things were getting electrified, homes were getting electrified, farms were getting electrified, and the farmer has those fences, those barbed wire fences they put out. And someone had the great idea back in the day to say, I wonder if I took a circuit out of that box, that electrical box that was in either the barn or the house, that was, lighting the light bulbs and things of that nature, maybe turning some things on the farm and from a work perspective, leveraging electricity for that. And they said, what they did was they would take a conductor through a few light bulbs to lower the current, and then they would use that and circle an area to keep their animals inside of a fenced-in area. And it seemed to work pretty good until they started to kill people. And then that is what happened. They had documented cases of children who would walk up to the fence because what? You've got a moo cow, right? That's what I used to call them when I was a little kid. I'd call them a moo cow, and I would want to go pet the cows, right? So you walk up to the fence, and what do you do as a child? You grab the hold of the fence to hold on. And what happened? Where they had documented statistics of children who were killed. So farmers were using this to bring in cattle, to keep the cattle in locations, pigs in locations, horses, etc. The documented cases from Salem, Oregon, in November of 1936, they recorded these examples, and I'm just going to read briefly through them. They had a 3-year-old girl come in contact with an electric fence, which was limited to an output of 25 milliamps, right? So how did they limit that? They limited that through those light bulbs, which was not provided with a current interrupter. She was unable to release herself from the wire until the circuit was broken. The same thing experienced a 21-year-old. And then they had a young man who was hooked up on about 18 milliamps of current. They had a dog that was killed, a 3-year-old boy that was killed in contact with a 110-volt fence. In series, there you go, with a 30-watt lamp. That's how they came up with knowing how much current that was possibly in the circuit. They had a 15-year-old boy unable to release himself from an electric fence, a 25-watt lamp that was in there, so they calculated about 230 milliamps. They had a few other examples. A 15-year-old boy unable to release himself from an electric fence. A cow was killed. Can you imagine, Nihad? They killed a cow. I mean, they had a 75-watt, 110-volt lamp. They calculated about 680 milliamps. So, when you look at these examples, you and I sit on, in which you didn't, I don't know if you noted, we both, Nihad and I both sit on Code Making Panel 2. Nihad is the IEEE representative on Panel 2. You've been on there one cycle so far, is that right?
2020 was my first cycle, so we're getting ready to start 2023. But
yep.
Yeah, I guess I forgot to mention that I'm lucky to serve on different committees of CSA and IEEE and NFPA.
So when you say, so you're on the CSA, you're on Canadian standards?
I'm on the Z462, which is 7E equivalent. I'm not on the Canadian electrical.
Okay.
So Z462 is a 7E, the Canadian version of 7E.
Gotcha. So when you look at these examples, and we sit on Code Making Panel 2, and what we will get is, we'll get, public inputs or public comments around expansion of GFCI, and they bring data to us. We just last cycle passed a few code requirements around GFCI due to shock. We expanded the upper limit. We took it from a 15 to 20 up. We just said any one of those, any receptacle outlet that's in any room will need to be, that's in that list of items in 210.8a, right? Will need to have GFCI protection. And the reason we did that was because of statistics. We had examples of children who were playing in and around a dryer, and they were killed because the dryer became energized. We have to realize that people should not have to perish in their home from shock when we have technologies to limit that. But what this did back in the 30s was it drove a manufacturer. It drove somebody to come up with the idea that to provide the solution that farmers wanted with this electric fence, but to limit the amount of current so that it wouldn't kill somebody. And they wanted to get it listed. So what happened was you had somebody, I say a manufacturer, I'm not sure if it was a full-blown manufacturer at the time who took this on, or if it was somebody who had the idea and then created a product and then wanted to sell it. And they wanted UL to list it. But UL was standing there like, well, how do we know what current will kill you? All we have are some examples, and we have thresholds of what we calculate that may have killed those individuals, but they really didn't know if the solution that was being provided to them to test would actually prevent somebody from being shocked.
Yeah, as I say, and to add to your point, Tom, a lot of this research was driven by insurance companies because, you know, the manufacturer, anyone, you don't want to kill someone in your property. Like even, you don't want to kill your animal, right? So insurance or fires, for example, a lot of fires that all drove the interest in, you know, in safety in general and just shock protection, that specific topic that we have today. But a lot of it was insurance driven.
Yeah, and so UL did some research, and you'll see this even in the research reports that we see today from UL Research Foundation or from their technical reports group. They'll try to help code making panels make better decisions based on research, and the process that they used back in 1939 is no different than what we see today. They did a review of accident records, which is some of the examples that I showed you were out of that report. And then they had to figure out what is the body resistance, because you know Nihad, we're engineers, and those who are on this YouTube or who are watching this are probably in the electrical industry, and we all realize that the amount of current that flows in a circuit is dependent upon Ohm's law. V is equal to IR. So I need to know the voltage, which they know. They need to know the resistance of the circuit to determine how much current will be flowing through a body. So they needed to determine the resistance of the human body. And they were focusing on children. And I think the next, I think I have in here their scope document. But they were focusing on from children to adults, both male and female. So they need, and then they needed to determine they needed to do tests to determine let go thresholds.
Yeah, as I say, the reason that they focused on children is back in the day they wanted to come up with I guess some like we're going to talk about this later. The boundaries of protection. They wanted to come up with limits that would apply to the majority of the population. You just don't want to protect, you know, adults. Healthy people and then forget about children. So that's why we have to make sure that our limits covers those are most vulnerable, and in this case would be children. So I believe this report was down to children 2 years of age.
Yeah, and if you look at some of these examples, they had a 3-year-old girl who came in contact. So their statistics and their research supported their effort that they needed to go down as to the small child all the way up to male and men, male and female individuals, grown-ups, grown adults. So in 1930, so we're going back to 1930, a series of tests was conducted by UL, which would probably not be permitted today. We have, back in the day, in those days, and we joke around, Nihad and I were talking about this on Friday that, hey, yeah, beer money and all that good stuff. And they did have beer back in the 30s. So they probably, we're paying some people to do these tests. But you'll see there were some actually company employees that some other companies other than UL did testing as well. I don't know if I think it was International Harvester or whatever it was. But what they did was they tested members of the laboratory staff that were used. So if you worked in that laboratory, you were voluntold that you're going to hold on to electrodes and they were going to pass current through your body until you couldn't let go. And I do have some videos of these, which I'm not going to show online now, but there are some videos out there floating around. And I would suggest that you get into one of the presentations from UL, because I know Dave Deeney and crew used to do these presentations and show some of those videos. They're funny. So, and then they recorded how much current that was passing through the body. Now, in in parallel with that, it was International Harvester actually that did some testing, and they did this with some of their employees, where they would take take a subject and have them try to pick up an object that was immersed in a bucket of water. They served from variable transformer was connected to a galvanized bucket, which was filled with water. The other side of the circuit was connected to a hand electrode, which the subject held. With the free hand, the subject then tried to pick up an object immersed in the bucket of water. So they said, hold on to this, stick your hand in that water, and then try to pick that up. So they did this to 22 men subjected to those tests, and they found that under those conditions, the maximum voltage an individual could withstand was around 12 and 20 volts. So
isn't it amazing? People don't know, and they just kind of do things that they're just not expecting the consequences. And like, yeah, it's not a big deal. Just grab this thing from a bucket of water.
Yeah. And I'm sure right before that, there was a here, hold my beer type of discussion, right? There was a Dr. Johnson who conducted the tests, and he noted that anything over 12 volts was extremely dangerous. And what's funny, what's interesting is he says anything over 12 volts was extremely dangerous, and they submitted their employees between 12 and 20 volts. So they definitely went over 12 volts. And for him to say it was extremely dangerous, I don't know what the results were of that test. But so the goals of this research in the 30s was safety for a 2-year-old child when exposed to contact with an electric fence. And they were specifically looking at it because, again, they were posed with a product that wanted to be listed to be used in this application. So they had to focus on that. But to do that, they had to determine the resistance and impedance of the body. So the purpose was to determine the maximum value and the nature of that current, which within certain limits of frequency. So they knew frequency made a difference as well, which we're going to talk about that too, Nihad, a little bit later.
Yeah. What's important? Frequencies. Yeah, we talk about this.
Absolutely. So voltage potential is important because that's how much that's what drives the current. Frequency they found was important as well. So and they did some testing, and if you read this report, which is they looked at the time the electrocutions, the death penalty, right? At the time when they would electrocute somebody, they took the data from those events and they analyzed them on how much current it took to kill an individual who was from a penitentiary perspective, from a what do you call that punishment, the ultimate punishment of somebody. The death penalty. So they took that data, but then they realized that that's not those are adults. We needed other subjects, and they established the conditions. So they take the basic condition would be a child barefooted standing in a pool of water or mud, and then falling across and grasping a wire with 2 wet or sweaty hands. And again, that fence would be a they wouldn't anticipate it being an electrical fence, so it's not like you're aware of that when you grab it. So that's sort of what they're representing and trying to figure out more information on. So they needed to understand the problem, understand the background of current through the body, determining the resistance of the body so they can calculate how much current would pass, and then determine the impact of current to the body. The outer skin, now this is important, and I can understand this. So an interesting thing they noted was, as a conductor, the human body is made up of 2 parallel paths. And what we know about parallel paths, when you put impedances or resistances in parallel, they'll add to lower the overall impedance, right? The Thevenin equivalent. The outer skin is relatively high resistance, but the bloodstream and the body tissue is relatively low resistance. So if you think about the bloodstream in your veins, etc., the challenging part of that path through the body is that those currents go through where? Your organs, right? So typically in an electrical shock example, you'll get organ damage because those are some of the lower impedance paths through the body.
So, Tom, to add to this point, the human skin is actually modeled as a high resistance in parallel with a big capacitance or a big capacitor. So, if you think of it, at low frequency, the capacitive reactance is really high because of the capacitor. It's really big
Mm-hmm.
there, so it's considered resistant. And that's why the body, we usually model the human body as a resistor, like Tom said. The internal is all fluid, so it's always resistant. It's lower resistant than the skin. But if you since Tom mentioned frequency, once frequency comes into play at higher frequencies, the capacitive reactance would have so it's not going to be an infinite value anymore. It has to be it will come into play in the equation. And actually, as the frequency increases, the skin resistance will turn into a capacitive reactance, not a resistance like it used to. It's kind of just with the frequency effect. Also, wet skin, like moisture, has a big impact on resistance. If your skin gets wet, it drops down the resistance quite a bit.
Yeah. So, um, what was interesting was they calculated that impedance of the skin, that resistance, and they said it was approximately 40 to 50,000 ohms per square centimeter. And then they said it drops. So then they recognized that when it gets when it's wet, when your skin is wet, your resistance drops. And now what I found interesting was, and that, we use tables like this resistance, and you have the finger touch, which is 40,000 to a million dry, and then wet is 4,000 to 15,000 ohms when you're wet. So you can see that resistance value change when things get wet. That 40,000 number aligns very well, and some of these other numbers align very well with what is in these studies from the 1930s. So this data goes as far back as tests that were conducted in the 30s, and helps us understand the amount of impedance and resistance for current flowing through the body. Now, we're going to reference this later, Nihad, but do you want to talk a little bit about this chart in regard to this, or do you think we should wait till a little bit later?
Well, I can briefly talk about it. So I just want to make sure that there are some numbers to the left of the chart. Just talks about let go threshold, difficulty breathing, fibrillation. Just want to emphasize, we're going to be, like Tom said, we're covering this in more detail later, but just want to emphasize that these numbers are average numbers, and they just cover, I would say, 95 percentile of healthy humans, like people with known medical conditions. But it's always a range. Like, for example, we talk about let go threshold. The chart shows 10 milliamp, but usually it's around 8 to 15 milliamp, depending on a lot of conditions, like your heart conditions, body size, age, gender. If it's child, will be a little lower, skin moisture, and all those kind of things. And then fibrillation. This is a very important limit there. It happens usually around 50 milliamp, but this doesn't mean that it couldn't happen at a lower amount of current, depending on the conditions. But this is kind of typically what they use. Difficult breathing happens around 20, 30 milliamp, I think. And this is kind of goes to the, would just help us to understand why we set the limits of GFCI or shock protection where they're at today. Based on those, again, there's all approximate numbers, average numbers. It's just probability, and this doesn't mean that it's set in stone. Like I said, it depends on the conditions and a lot of other things.
Yep. And I'm looking at the chat on YouTube, and it says David Engelhardt said that the Land Development Code in his jurisdiction prohibits the use of electric fences, which is really interesting. I didn't know anybody did that. I didn't know anybody prohibited. I know there are a lot of farms around where I live have the electric fence. In fact, when I was a kid, this reminds me, when I was a kid, I was with my brother and my dad, and we were groundhog hunting. I had braces at the time, and we were sitting at the edge of the fence, and my brother was taking a shot on a groundhog, and he hit it. And when he took the groundhog, I went, "You got it!" And I put my head back, and I hit that electric fence. And I'll tell you what, Nihad, I saw stars. I thought my teeth were gonna fall out, and I didn't have any burn marks. I didn't have anything on my body which would indicate that I was shocked. But I'll tell you what, those fences are very powerful, buddy. Very powerful.
I'm glad you're still here with us, Tom, because this sounds like a near miss.
Yeah,
For sure.
yeah, a near miss, but it was safe, right? It was safe. So now, in when they did the tests for the body electrical resistance, what they did was the individual, you know, I the individual that they don't want to name names, right? Immersed their hands in and feet in 20% solution of sodium chloride prior to grasping the hand electrodes and prior to standing on the foot electrodes. So they actually tested between hand and foot, hand in hand. They did the let go thresholds. I believe they would hold an item and put a band around their bicep, and have current go through their forearm, and try to get them to let that go. So they did preliminary tests. The body resistance is independent of the value of current employed between 1 and 15 milliamps. A constant area and pressure of contact were maintained in all the tests. They provided the individual wet his hands in the solution each time prior to, so they had to have the conditions right. They had to hold it at a consistent throughout the process. And because, how much pressure, how much, I guess, flesh you have in contact with that electrode made a difference as well. They derived the current from a 12-volt dry cell battery, which were connected directly across a 3,000 ohm series resistance. So they limited the amount of current. And I think they had a potentiometer in there well to vary the resistance. And then they calculated based upon the readings that they had. The hand electrode, they had a number 10 bare copper wire twisted together and supported approximately 6 inches apart on a porcelain insulators. I mean, just the description, I wouldn't grab that wire, right? The foot electrode was a copper plate, 30 gauge, approximately 14 inches square. So, they set that up, and the body resistance from hand to hand. So they tested hand to hand and hand to foot. Individual firmly grasped the electrodes with both hands, and they previously immersed in the brine solution. From hand to foot, they would hold that they put their foot on the copper plate and then hold the electrode in their hand. So
I don't know what you would think about this test. What do you think, Tom?
Oh, you know what? I would not think about this test, but here's what they did, Neha. This is the interesting part, was they did all these tests and if you look at the tables that they have in there, they have the ages of the individuals. They have their age, they have their race, they have the male or female and all those little statistics, and they have the amount of resistance, etc. But they said, it's not enough. We need to do these same tests upon children, as the data did not indicate whether resistance of children under those given conditions would be greater or less than the recorded for the adults. So they said, what? We need to go find some 3-year-olds all the way through 15-year-olds and do those same tests, and they did that. I don't know. I don't know if I'd let my kid do that, but they did. So they had resistance.
Right? It was a different world.
It just gives me the EBGBs, that they would. But they were healthy individuals, and it was a controlled experiment. Now this conclusion is, and I think you and I talked a little bit about this, but what I found interesting was that they said it was assumed therefore that the lowest body resistance, they said that the study tabulated data show that the body resistance of children under the conditions of measured is higher than of adults measured under the same conditions. Now, I scratched my head trying to think, why would a child's resistance be higher when they're so much smaller, right? And the only thing I can think of, Neha, what?
I couldn't explain one either. I just couldn't. It's just, it's against what we know today. And because we always say that children are more vulnerable to current because they have lower resistance, smaller body mass, lower resistance. Yeah, this conclusion that I couldn't make anything out of it. I don't know why.
Well, the only thing I can think of, Nihad, is that when you have, we all know that that current takes all paths, right? And if I have resistances and impedances in parallel, then it reduces the overall impedance. The only thing I can think of is that the more mass that you have, the more, say, saline solution or salty solutions that you have in your body, the more paths for current to take. Those parallel paths may provide a lower Thevenin equivalent of of an impedance for the body than a child who has, lower mass and less paths through the body for that current to take. But I can't explain why their results showed that the body resistance of a child was greater than an adult. But they came up with basically that in connection with the electric fence application, that the resistance, the lowest body resistance that they would use is 500 ohms.
Yeah, typically it's between 500 to 1500 ohms, like 1.5K.
Yep.
Yeah, so this is kind of the average. Of course, assuming that the skin is not wet, because if your skin is wet, like I think Tom will be touching on this on Tuesday, no, maybe Wednesday, that we'll be talking about marina, electric shock drowning. Once your skin is wet, your body resistance drops tremendously. It could be like 100 ohms or something, 200.
Yeah. Now, Don Ganir made a good point. He says that a child has less surface area in contact with the test electrodes. So, Don, they have less surface area. So you would think that they would have less impedance, but I don't know. I don't know. It's just it's a mystery to me. And anything that we say is really probably, it's all theory until we test it. So, Nihad, I think maybe as part of the Shock Week, we, Jim Dollard says, he told me, he says, you know what, I'll do Thursday's presentation as long as we can shock somebody. And I'm like, well, I don't know about that. I know he was joking around, but maybe I'll take him up on that and see if I can get him to maybe prove some of these theories out. I don't know.
So tell Jimmy Dollard you get a mug if you get shocked. See what he says.
Yeah, there you go. Now, here's another interesting thing. We talk about frequency. So in 1900, Prevost and Batelli found that alternating current potentials as low as 15 to 25 volts at a frequency of 150 cycles caused death of dogs. So they were doing tests on dogs as early as 1900, 30 years before this test. And another name that I don't know if it's in this one or on the next slide, but I know Gilbert pointed out that European technicians have established the fact that circuits of potentials of 20 to 24 volts are definitely dangerous to animals. They said 24 volts. So in a particular case, it was stated that a potential gradient upon the Earth's surface of 10 volts was the cause of a death of an animal. So there's your, what do they call that? Earth leakage and whatnot, right? Step potentials, etc.
Oh, yeah. Touch potentials, yeah.
Right,
you have
right.
a slide on it.
Yep.
But
So
to the point of frequency, I'd like to add that, back in the day, if you look at the history of the DC-AC war and how we picked, because I like to learn about history, and I've always had this question, why did we pick 60 hertz in North America and like Europe and the rest of the world? Like I grew up in Egypt, in Cairo, Egypt, where I was born, and it's 50 hertz, right? I've always wondered why we picked the 50, 60 hertz. There was a great paper that I read, I think it was an IEEE magazine, talks about the history, and turned out there was very random. There was no scientific reason behind 50 or 60 hertz. But interestingly enough, and when they picked this frequency, the 60 hertz or 50 hertz, they did not know that this is the worst frequency that you could ever pick in terms of the human body, because 60 hertz, 50, 60 is the most dangerous frequencies, because the heart frequency is very similar, is very close to 50, 60 hertz when pumping blood. So 50, 60 hertz has the worst physiological impact or effect on human heart, because the frequency, you're hitting the heart with a frequency very close to its frequency that it just pumps blood at, and this would mess up the whole thing. So I guess as a result, to get into fibrillation, you would need more current at higher frequencies. And I think around DC, it's roughly, they always say that's roughly 10 times more. So 6 milliamp, for example, you would require something close to 60, maybe 50 something to get to fibrillation, the same impact that 6 milliamp or 5 milliamp would do at AC 60 hertz. And if it was, let's say, 400 hertz or 1 kilohertz, you would need higher current to get to the same physiological effect of fibrillation. So just
Interesting.
like they
Interesting.
picked the best, yeah, they just picked the best number in terms of safety. But again, they didn't know back in the day when Edison was going against Westinghouse, Tesla, and all the stuff. They just didn't know. They just picked 50, 60, and it was the worst frequency in terms of fibrillation to the heart.
Interesting, yeah. And they did, I mean, so as early as the 1900s, they did actual testing on hearts and things of that nature, and on animals. Tuse is an author on medical electricity, said that 10 volts applied for a period of 1 second would produce fibrillation. So that's interesting to say 10 volts for a period of 1 second. So they knew that current and the amount of time that it was permitted to flow through, in that case, the heart, would cause was a factor. So time was also a factor. Now
Time is a big factor. We're talking about this too. It's very important.
Yep. Now this is interesting because I see a name in this laboratory test in this document that I recognize, D'Arsenval, and I believe D'Arsenval made some meters, and he invented a lot of things in the electrical industry that we've used and as a basis for a lot of probably the tools and meters and things that we use today. But in 1892, he subjected himself to 3 amps without any effect from a frequency range from 4,000 to 1 million cycles per second. So you had a guy like D'Arsenval who was testing on himself with I wonder who turned it off if there was a problem, but that's, I'm just going to put that on the side. But you have, this really shows you that there was a lot of testing done back in the day on human beings, on people, and in case of D'Arsenval in 1892 on himself, when electricity was coming to our society, our world. Now, they said that in view of the scarcity of data pertaining to short duration shocks on direct current and the lack of data involving frequencies higher than the commercial 60 cycle per second, no warrant for permitting greater values of current than indicated regardless of the frequency employed. So they talked about, we have limitations in the 943 and based upon testing of where we go from a frequency perspective. And we'll talk about that a little bit later in our presentation as well in this discussion. So this, when you look at, this is like some of the continuous current data that we talked, that they did. And you'll see some references in here to 30 milliamps to 20 milliamps. 15 milliamps, and I know the 4 to 6 milliamp numbers are in here too. There's the minimum recorded value was 6 milliamps, and the average for 13 subjects tested was 7.8 milliamps. So we're getting some indication that of the numbers that we know and we associate with GFCI protection as you look through some of the test data from the 30s. And moving forward, even in later on and I have some other reports too that we can talk about. So yep. So again, 1855 electrodes 15 to 30 milliamps. So there's a lot of history, a lot of data, and here's some of the last couple things here from a conclusion. They said that a maximum current, uninterrupted current, to which an individual may be safely subjected is 5 milliamps. Now, we know GFCI, and this goes back to the 30s, we know a GFCI operates anywhere from 4 to 6 milliamps. So we have a minimum of 4 and a maximum of 6. So there's your operating region right around 5 milliamps. So that 5 milliamp number comes from the 30s and earlier testing that was conducted on people.
So, Tom, yeah, this is a very good point. And they refer to this as 5 plus minus 1. Because it's 5 milliamps, so your lower end is 4 and your upper end is 6. In the industry, we always say 6 milliamp, but it's technically 5 plus minus 1. And when you design a GFCI, you never trip at 6 because there's temperature deviation, conditions, whatever. So you try to design your device, a GFCI, to trip somewhere between 4 and 6, not at 6 or not at 4 because it could drift because of temperature whatsoever. The other point I wanted to make is the 5 milliamp, when they say in this conclusion that is the minimum uninterrupted current to which an individual may be safely subjected is 5 milliamp. They meant by this let go threshold, which means, like Tom mentioned during one of the slides, that at that point, at that current, such a low current, the individual is able to uh, disconnect or disassociate themselves from the circuit, like let go the circuit. Because if you go higher than this is like the let go threshold, like around 10 milliamp, muscle contraction happens and you won't be able to control your muscles anymore. So if you try to let go, let's say you're grabbing a wire or touching a faulty equipment, you won't be able to because you lost control over your muscles, which is actually the reason for electric shock drowning that Tom would be discussing in marina. Because as a swimmer, you'll be in the water and you just can't swim anymore, so you sink, thinking that people think it was just someone drowned, but really it was a shock that caused this whole problem. So, and this is, I wanted to emphasize this because this is the main, the fundamental difference or psychological fundamental difference between North American shock protection and Europe. Some of you on the call might have heard RCDs, residual current device, which RCD is the European version of GFCIs. And those devices, if you're familiar with, they trip at 30 milliamp, 20 to 30 milliamp. And the reason is, in Europe, they decided that they're going to protect people against ventricular fibrillation. Remember, we said ventricular fibrillation is around 50 milliamp, roughly plus minus. So they went with the 20 to 30 milliamp trip level because they only provide ventricular fibrillation protection. And if you are stuck, someone is stuck to a circuit, they don't protect, they don't allow let go protection because the device would interrupt the power for you. On the other hand, in North America, because GFCI's Class A that we'll be talking about in very shortly here, was mainly designed for residential applications. So you don't want to take this risk of, women, children, to be shocked and not being able to let go. So that's the reason that we decided to go with the 5 plus minus 1 milliamp to even at that such low level, the device would interrupt power, but the individual would still be able to let go of the circuit or just disengage from the circuit as well. So this is kind of the difference. If someone was wondering why in Europe they use 30 milliamp and we use 6, the resistance body is the same. It doesn't change from North America to Europe, but this is just the reason. It's like a more of a fundamental difference, like philosophy, I guess, a different philosophy of protection.
Right. And to your point, this is let go related, not defibrillation. So uninterrupted current through the body, 5 milliamps, is not going to set your heart into defib. It's just going to be that you can't let it go.
But then the device is supposed to interrupt power, so it kind of lets you go, like you said, disconnect power if something goes wrong during the test. So this is kind of, it's like you have your, like Tom, you talks like one of the, in one of your presentation, Tom, you talked about the spotter, like the guy helping you lifting the heavy weight with the overcut protection. So you can think of the GFCI as the same thing. You can let go, but at the same time, this device is there to interrupt power, even if you can still let go. For RCDs, they don't have this concept. They just interrupt power when it gets closer to the fibrillation limit.
Right. And what they concluded for this specific product for the electric fence is it shouldn't exceed 4 milliamps. And they put a time limit, so it's a pulsed electrical signal that goes through that wire that won't pulse long enough to hit that let go threshold. So if you're walking by, you grab that fence, you'll feel that WAP, but it's not going to kill you. It's not going to go to put your heart into defib. It will be a lower value than the let go, so you can let go of the fence, and it's only going to pulse it for 0.1 and 0.2 seconds. So I thought that's a really interesting thing because what they did was they had the incidence of electric shock. They did their research, they did their testing, they came up with their conclusions, and they said, look, here, if you're going to have this product, then this is the product that you need. This is the criteria that you will need to pass, and that helped prevent electric shock in and around those farms. So from an historical perspective, you had the evidence of electrocutions back in the day, and they changed the industry. They changed how the entire electrical industry by the parameters that and the research that they did, which we still use today, and products. They influenced the design and development of products that we continue to do today. Now, today's incidents, in my opinion, the the beginning of another era in ground fault circuit interrupter protection. And you raised this, Nihad, a few minutes ago. We've got the evidence of deaths in and around marinas. We know electric shock drowning is a very recent term that Mr. Ritz, Lucas Ritz's father, helped discover because of Lucas's death in a marina. And if you don't know Lucas's story, I'll put a link to his story below when this YouTube video is posted, because I think it's worth your time in watching and learning about Lucas's loss of Lucas in a marina, because there's I think that is really spurred. There's code changes around it, and I know there's research and development going on right now to help understand what we can do to help reduce the likelihood of deaths in and around marinas due to electric shock drownings.
It was a really sad story, but it was an eye opener because I learned about Lucas and then all the other incidents a few years back, and it was like, wow, this is just something that you'd never think of. But yeah, it's a real hazard, marinas.
Yep, and there were some changes. Myself and Joe Engel, or not Joe Engel, Joe Fellow, we put together some public input and some public comments in the 2011 cycle, and we got the code making panel to make some changes and adding ground fault protection in and around marinas, and that continued. That spurred some research, and there's an NFPA Research Foundation reports, etc., and that will continue. So the journey of GFCIs is just begun for marinas, and I think a lot of the testing that will continue moving forward. Now,
absolutely, yeah.
All right, Nihad, we're into phase 2 of this discussion: boundaries of protection. So we talked already about the experiments with animals, the information available from clinical observations, etc. We know a lot more about shock today than we ever did before. And we know that there are 3 key things that impact the severity of shock on a human being. The first one is magnitude. And we already talked about that. We talked about the thresholds of 4 to 6 milliamps. We talked 30 milliamps. Other different magnitudes of current, but we didn't talk about how much time that current, nor the path that the current would take through the body. So we know the amount of current that flows through the body, the path that it takes through the body, meaning your chest cavity is your worst place because of your heart. And as Nihad pointed out, it's your heart, it pulses and changes. It's an electrical circuit that operates, unfortunately, right there around 50, 60 hertz. So we're in sync with that same frequency of your body. And then the important part is the length of time that we let current flow through the body. Now, let's talk about each of those. The magnitude of current we already talked a lot about is driven by basics of Ohm's law, the amount of voltage and the impedance of the circuit. We noted, and Don Ganier noted earlier when we were... he commented, Don said it looks like they used the operating resistance of the incandescent lamps to calculate the current, limiting on the fence. And he mentioned that cold resistance would be much lower, passing a lot more current. So temperature impacts the amount of current that will flow because it will impact the amount of impedance in the circuit. We know based on from the research and the studies that we've been looking at, that they looked at in the entire circuit. So voltage and current is going to determine that, and we know that the magnitude of current will get tingling sensations at somewhere between 0.5 to 3 milliamps. As you increase current through the body, you'll start to get those muscle contractions. And Nihad, I'm gonna put the link to this down below. But the story, there's a video of Lucas's brother talking about the day that Lucas passed away. And he said he was in the water and he was swimming towards his brother in the water. And he said he felt a tingling sensation. And in my mind, he was probably getting 0.5 to 3 milliamps flowing through his body. And then he said as he got closer, he felt the water pulsing. And it wasn't the water that was pulsing, it was his muscles that were starting to contract. His mother noted that when she jumped in to get Lucas, that the moment she hit the water, her muscles contracted and she could not move. And she was lucky that she was holding on to Lucas's life preserver because she was basically immobilized, and she was thinking it was because of the adrenaline, it was because of the what was going on at the moment, but in reality she was close to the source, so she was beyond the let go threshold of around 10 to 40 milliamps. So
You know,
go ahead.
Tom, the way it works, it's actually like the source kind of sets up an electric field, and it's more like concentric circles. So the closer you get to the center of those concentric circles, the more physiological reaction or impact you'll be receiving. So I would say Lucas's brother was at the very far end of like those concentric circles. That's why he just felt the tingle. But if he would have tried to swim further into the closer to his brother, who obviously was in a closer concentric circle, he would have had more impact. Like the mom probably had, like you said, the let go threshold because when she jumped in, she was closer to the center of the source. That's why it's probably that's what happens. Yeah, and the problem is the other challenge with the electric shock drowning. Since we're bringing this up, it gets very it's almost impossible to figure out what happened unless a family member or a friend witnessed the incident, because autopsy won't show it. Like if it was after the fact, autopsy would just show that this person just drowned. There is no way that you prove that there was a leakage in the water or in the marina that caused the drowning. So there's a lot of cases people believe a lot of cases just go under the radar because no one was there and autopsy won't catch it. So the numbers, I would probably expect them to be much higher than what we have, and the numbers we have today are staggering in terms of electric shock drowning.
Yeah, and in Lucas's case, if his father asked the question, what happened? Okay, he wanted to know why his child died. He had a life preserver on in the water, and he something invisible killed him. So he asked that question why, and the coroner's report initially came out that Lucas drowned, and his father pushed back saying, look, he was wearing a life preserver. And probably the only water in Lucas's in his lungs was probably due to just getting him out of the water and things of that nature. So he pushed back on it, and that's how the definition of electric shock drowning arrived, because they realized that he was really electrocuted, but there are probably so many other people, to your point, that drowned, and they were categorized as a drowning in and around a marina, that they drowned because they were immobilized and they just sank and they could not swim away. So
we were really lucky in case of Luke. I mean, it was like I said, it was an unfortunate incident, but Lucas's dad, if I remember the story correctly, was an electrician, and that's why he said, you know what, I'm not taking this drowning as an answer, and he went and investigated. I remember in the article he described that he went and measured. He took some measurements around the marina, and then he found that one of the boats at the harbor was leaking. And when they traced the whole thing, they found out about this, electricity leakage current coming from the boat. And I guess this whole thing unraveled because one dad, just wouldn't, just take drowning as an answer, because I'm sure there's a lot of people prior to Lucas had the same thing, and the family just didn't know. Okay, he drowned or she drowned, and it was just unfortunate. But luckily, his dad, Lucas's dad, was an electrician, so he was able to, take some measurements and find this hazard that no one was aware of.
Yep. And some of the, again, a lot of what we know today, this is the electric shock as it pertains to the electric fence. That was one of the oldest reports which we reviewed. We had this table which we already talked about from a resistance of the body perspective, because that's how we determine how much current flows through the body. If you do Ohm's law, V is equal to IR, so I is equal to V voltage divided by resistance on a 120 volt circuit with 500 ohms, which is that 500 ohms is what we saw earlier in that UL test report from the 1930s. From that testing, that for a 120 volt circuit at 500 ohms, if they put that just across that human body, it's 0.24 amps, so 240 milliamps would flow.
So just remember this 240 milliamp, because we'll be using this equation later in one of the slides, but we are going to be increasing the voltage 120 volt by 10%, because this is the number that the range that UL uses for testing GFCI. So if you increase the 120 or multiply it by 1.1, 110%, you actually get 264 milliamp on a 120 volt circuit. And I guess, I don't know if we mentioned that before or not, and kind of maybe we did. I just want to emphasize that current is what what kills people, not voltage. Like, I'm sure you heard of stories, people getting shocked just playing with fixing something on their car, or just like such a low voltage. So the misconception is, oh, it's low voltage circuit, I'm safe. It's current and the path of the current where it hits your heart or not. So it's not the voltage that kills you, it is the current.
The amount of current, the path it takes through your body, and the amount of time we let it flow.
Exactly.
Yep. And that brings us to the path, right? So, again, this is the critical area, is right there in that chest cavity. And so hand to hand is probably your worst case, even your hand to foot, because it's going to flow through that chest cavity. The path that takes through the body is important. And Charles Dalziel did a lot of testing back in the in late 50s into the 60s. And he established, again, I guess in my thoughts, he built upon the previous UL studies that were done in the 30s. And I think he probably is the one who is he is the one who's been recognized. We hear the Dalziel curve referenced. We hear his name thrown around, but there were a lot of research done even before Dalziel did his in 1960s, and what you're seeing here is they're testing the perception on the current on the tip of his tongue. So he's holding an electrode to his tongue, and in this case, what they would do is they would put in a electrode band across his arm, his forearm. And then he would hold something in his hand, and they would pass current just through the forearm to determine the let-go thresholds. And I think a lot of his data basically supported what was done in the 30s, and then he probably added on to all of that test data that was already there.
Tom, can we go back to the path slide? Because I had a couple of quick comments on the path before we get into the time. Just I don't want to interrupt your flow.
Go ahead.
But, yeah. So yeah, sure. So I just because I figured we mentioned this because we talked about it a few minutes ago. So the first path, which is hand-to-hand, this is what we refer to as touch potential. And like Tom said, it's very dangerous because it goes right through the heart. And then the second path is like the leg-to-leg is the step potential. And this is very, you can see this at a lot of the power stations and high voltage power stations. Like if you step, you kind of take smaller steps wherever. If there's a power line down, and they always recommend that people don't leave the vehicle because there is a potential electric field on the ground. And the bigger steps you take, the more potential voltage, potential difference across your body. And then the third and fourth paths are what they refer to as the combination between touch and step. So it's touch and step potential. And as you can see, the least dangerous case is case number 3, because the current is not going through your heart. It just kind of goes from the right hand to the right leg. It misses the heart. Doesn't mean it's not dangerous, but the danger is less because probability of fibrillation is less because the current is not hitting the heart. And this was the trick. I guess the reason I always heard this trick, like electricians back in the day were trained to use their right hand, even if they were left-handed, when they were dealing with electricity, because in case if you get a shock, it doesn't hit your heart. Because they're hoping that you would have the path number 3, in the slide, that the current would go through your right hand, through your leg, and kind of misses your heart.
Good point, Nihad. I'm just looking at the chat.
Go back, but
I'm sorry?
I said I'm sorry. I had to ask you to go back. But
no, not a problem. So I'm looking at the chat session. Jim Dewig is asking, what is the source of reference for the current level reaction chart? I think what he's speaking to is this chart right here. And I believe this chart, this tingling and the muscle contractions I believe stems more from Dalziel's testing than it does from the 1930s, because I know the 1930s talked about the muscle contraction, and they have the thresholds documented in that 30s report. They definitely have documented the let go threshold, and I think that though that the combination of all of this data is from that 1930s report and Dalziel's report, and possibly there's probably a few others in there as well that supports that.
Tom, I would agree. I think this chart is a product of uh, various or multiple research, like Dalziel, the stuff that was done in the 30s. IEC did a lot of work, and we'll be talking about that IEC chart, I believe, in the next slide. So this is just, I mean, I can't really pinpoint to a specific research. This probably, the collaboration of different studies and experiments done by UL, Dalziel, and other people. We just always talk about Dalziel because his research or work is the most popular, but there are other people that did research on shock as well. So I mean, in Europe, IEC did a lot of work as well. So I think it's just a summary of everything that the knowledge that we have today.
All right. So why don't you walk us through this this chart, because I know you've done a lot of research on this, and I'm gonna get it to I'm gonna populate a few of the text, and then you can why don't you lead us through this discussion?
Sure. So I can do this. This chart is, the source says, it's based on IEC 6479, part number one. Dash one is part number one. There are three parts of this standard. And the standard title is the effect of electric current, 56 electric current on humans and livestock. So part one talks about 60 hertz, 50, 60 hertz. Part number two talks about higher frequencies. There's some, similar stuff, but they did more testing on higher frequencies. I don't have all the background research, but I have the standard, and this is what they reported. So you have the vertical axis and the horizontal axis. Horizontal axis is the current in milliamp, milliamperes passing through the person's body. And then the vertical axis is the time, the duration of current passing through the person without being interrupted in milliseconds. And they have four different regions. Like you can think of this whole curve as four different regions. The first region is the green, light green, which is like the vertical line A. And this region is like it's below 0.5 milliamp. And this is just imperception. You won't even feel the shock if the current is less than half milliamp, or sorry, 0.5 milliamp. And so this is just like nothing. But then you start gradually feeling the harm, and you start like tingly feeling, and you get to the point of like muscle contraction, like we said, as you go further to the right. So the more of the I guess the orange area is no harm area, like there's not going to be any dangerous. But you notice that the region A, there's no time impact. It's just like a vertical line. It doesn't matter how long it takes for 0.5 or less milliamp of current going through you. There is no impact whatsoever on time. But when you get into the no harm region, you see like there's a vertical 5 milliamp line. If you extend this line all the way vertically, it goes to line B, like at the top of the chart. And Tom, like exactly. Thank you, Tom. I'm just gonna say if you can extend it. So the 5 milliamp meets the line B. So if you think of anything less than 5 milliamp, like the region to the left of the vertical line of the 5 milliamp, it's independent on time. Again, it's the same thing. There's no harm. You can still let go. We talked about this. You can, disengage yourself from the circuit, and there's not that much harm. But once you go above the 5 milliamp, then time becomes a factor. You notice that the line, there's like a straight line going down, and this is the border, or the border between the no harm zone and the more light red zone, the muscle contraction. And if you, let's say, go at the 30 milliamp, because this is the European limit, if you go vertically up, I think around 400, maybe 400 milliseconds, you hit the borderline between the no harm zone and the involuntary muscular contraction zone, which means if the current is flowing through the person's body for more than, let's say, 400 or 350 milliseconds, then you get into this light red zone that is more dangerous than the no harm zone. And if you go to 100 milliamp, you notice that the vertical line, you meet the border between the two zones at less time. Looks like maybe 20 milliseconds or something, plus or minus. Like I guess Tom is just trying to add the vertical lines. So the point is, if you allow the current to flow more than this amount of time, then you would be transitioning from the no harm zone to the involuntary muscular contraction zone. And again, I would emphasize that this is not set in stone. Again, this probability depends on the heart condition, the health of the individual, being shocked, age, body size, and the moisture, the degree of the moisture on the skin, and all those kind of things. So this just, this chart covers like 95 percentile of the population, healthy population with no physical condition. And as you progress to the right, there is the darker red zone that has the C1, C2, C3 curves, and it's the ventricular. This is when you get into ventricular fibrillation, and you can see that the time is not almost instant as the current increases. But the C1, C2, C3 curves, what they show there, it's the probability of ventricular fibrillation. So if you're in the zone between C1 and C2, like this kind of narrow band between C1 and C2 curves, there is less than 5% probability of ventricular fibrillation. If you move to the curve in the region between curve C2 and C3, then you are getting into the less than 50%, of course, more than 5% and less than 50% of the probability of ventricular fibrillation. Anywhere to the right of C3, like I guess left there, exactly like Tom is showing, this is more than 50% of ventricular fibrillation. Like you can see, it's not set in stone. We can say it's definitely going to happen. Like there's 100% chances of ventricular fibrillation, but it gets higher than 50%. Again, depends on so many other factors. But of course, no one wants to risk and get into this region. That's why, if you notice, and I think the next slide would show this, we try to keep our protection limits in the no harm zone, the 5 milliamp. I hope this kind of explains why the 5 milliamp came into existence, because of kind of the UL curve matches. Try to kind of match this curve and keep the response in the orange area. So the power is interrupted before you don't allow the current to pass through a person long enough to get into the red, the light red, or the darker red regions for sure. You just want to interrupt the power in the orange area.
So the U.S. region of operation is above that 5 milliamp threshold, which again, I always used to say, before we wrote this IEEE paper together, I used to say after 4 to 6 milliamps, your heart goes into defibrillation, but that's not technically true. You go into the let go. It's not until beyond 30 milliamps that you start to get into beyond the let go threshold that you'll get into that chances of ventricular fibrillation. But do you know the number for that C1? I don't have that. Like if I brought this down, it's greater than 30 milliamps, isn't it?
It is greater. And and this explains the reason. Remember in one of the charts we said roughly it's around 50 milliamp ventricular fibrillation, plus minus around 50. And this explains again the point that I raised before, that in Europe, RCDs, like European version of GFCIs, their trip level is between 20 to 30, usually 30 milliamps, because again, if you think of it, if you interrupt power quick enough, you're still in the orange zone, even if you don't start reacting or detecting leakage current until you hit the 30 milliamp. Because like Tom said, showing the vertical line, the 30 milliamp, you're still in the orange zone, provided that you trip quick enough, like you don't get into the the red, light red zone. Just gonna have to make sure that your device detects the leakage current or the current going through the person's body and interrupt quick enough, so you're still in the no harm, no permanent harm. And of course, you feel a zap. Like don't get me wrong. Like if you're in the orange area, you still feel a good zap, but it's just not going to be harmful. Like there will be no medical attention required.
Yeah. So the other important thing to remember too, and I'm just trying to understand this a little bit myself here too, Nihad. The GFCI does not limit the amount of current that flows through your body, right?
No,
so
no.
This is just a threshold. Now, if my circuit, I'm trying to lead the witness, because you explained this very well, and because we had this exact same discussion when we were early on in our paper. My comment to you was that the GFCI does not limit the amount of current, and this is just a threshold. So from a European perspective, to your point, they want to trip fast enough so that you don't encroach and go long enough, let current in long enough to where you go into the involuntary muscle contraction or into defib. But if I have high fault currents based upon the impedance of the circuit, I could have higher fault currents, and because the GFCI does not limit the amount of current, I could still see, how many amps go through my body based upon the circuits that I'm in. So,
Tom, this is absolutely correct. I would say, remember the few slides back, we talked about the three main factors. There are other factors, like we said, but the three main factors are the amount of current, the path of the current, and time. Amount of current is controlled by what? Ohm's law, right? Like I think Tom showed in one slide, it was very good explanation that the current is based on the voltage and the resistance, the body resistance of the person. We can't control the current, the amount of current when there is a shock incident because it's controlled by the voltage of the circuit, 120 volt, 480 volt, whatever the circuit, the voltage of the circuit is, and the impedance or the resistance of the person. So current is out of the equation. We can't control current. GFCIs do not limit the amount of current going through a person's body. The second factor is the path. We can't control the path, right? It could be a step potential, touch potential. How can we control the path? We can't. So the path is out of the equation. The only factor that we can control to limit the physiological damage on a person is time. And this is what this chart is trying to show. If we interrupt power quick enough, then we are preventing, or maybe we can't eliminate completely, but we're minimizing the impact of current on the person, the severity of the shock, because we control time. We can control time, but we can't control the amount of current nor the path of the current. Yep. These are controlled by the conditions of the incident and the voltage of the circuit, the person's body impedance, whether it's wet or not, and all this kind of thing, the moisture levels.
Yeah. And so this is the curve. This is where how fast, remember, we have current in milliamps across the bottom. We have time up the left-hand side. This is your threshold where the heart would go into defib. So it's a different way to look at that same table, that was the chart that we looked in the previous slide. This is the UL standard limit that you're permitted from a UL perspective based upon the equation. But this is the typical reaction time of a GFCI, and that's purely because of the mechanical nature of the device, which we're going to get into now on how these things operate and how they do what they do, and how fast they operate. So that's typically where you're at in regard to where your heart would go into fibrillation. So the GFCI does not limit the amount of current that goes through your body. To your point, Nihad, it just operates at a time period fast enough that even for those higher currents that may be passing through your body, your heart's not going to go into defib, and you're still going to be able to let go.
And Tom, this is a great chart because this chart is a different way of sharing the same information that we just discussed. The top, you just try to be under the fibrillation, the heart fibrillation level, which is the green curve. And this is the UL defined curve for GFCIs. And by the way, this is a tri-national harmonized standard. So it's the same curve that we use in Canada, US, and Mexico. It's the same curve, class A. And we'll be talking about other classes, but this is the green curve, is the class A. I just want to indicate a quick thing here in this chart. Tom showed that typical class A GFCIs have this trip level. And you notice, as long as to be listed to meet the certification requirement, the device must react quicker than the UL limit. So you can think of this green curve as the envelope or like a boundary of operation. As long as the device's response is less or below this green curve, you are good to go. You don't have to meet the exact curve. The exact curve is the absolute maximum permitted amount that UL would allow. The other thing I would say for typical class A, because most of them are used in residential applications, we don't really have a curve. We have more of a like a definite time response around 15 millisecond, I believe, just like Thomas is showing. It's just a straight line. It doesn't matter what the current is. It would trip at the same amount of time. And this would actually cause what it's unfair to GFCIs, but a lot of people would, and I hear this all the time, they hate GFCIs because they nuisance trip. They just trip all the time. And the reason that they trip all the time is because if you have any inrush current, and if you're using this in an industrial setup, this is not a problem, like in a residential household application. But if you are tripping, if you're using this in a noisy environment, there is inrush currents, then you are still responding at the same time response or same speed when there's higher current. But the beauty of the green curve of UL that it allows more time at lower current, because this would help the device to override some of the like noise or inrush current or whatever stuff, that transient stuff that could happen when you're starting or turning on and off some motors.
Excellent. So now we're going to get into how these devices. So I have with me, Nihad, I've got a receptacle type GFCI, and actually this is an arc fault ground fault device, and this is a circuit breaker. So these types of devices have similar technology inside of them, and so what we're showing here is the circuit that we have this being the device here. Inside of this device, there is a coil, a current transformer, so to speak, a CT, that basically you're hot and you're neutral. Or if I have, like in this case, a 2-pole GFCI, I have both hots and my neutral that goes out to my load, all going through that one, I call it a donut, but it's a current transformer. All your conductors go, and it works on a basic principle of what goes out has to come back over the intended path. So if I am in a two conductor, a black wire and a white wire, a hot and a neutral, I have my equipment grounding conductor, but no current is supposed to go over that equipment grounding conductor at all. Everything has to stay in the path. So everything will go out on this conductor and back on the neutral, basically on the grounded conductor. And it goes through the donut, through that current transformer. And as long as everything goes out, everything that comes back is what went out, I get zero current as a difference. Nothing happens. But the moment I have a difference of current going out, then coming back, if I vary from that 4 to 6 milliamp threshold, somewhere in there, that's when the solid state circuitry tells the device to open.
Absolutely. And this is just this is how the general theory of operation applies to breakers, receptacles, or even some industrial version that we'll be talking about, 3-phase, single phase. As long as you have all your current carrying conductors going through the donut, the current transformer, CT, sometimes it's called zero sequence or core balance current transformer. The magnetic effect, it works on the magnetic effect of current. So as long as all the current going one direction is returning, all the current magnetic effects would cancel each other, and there will be no induced voltage on the secondary of the current transformer. Once there is imbalance, even if it's a slight imbalance, then this cancellation is not there. There will be a differential magnetic field, and of course you have a second, like at any transformer, you have voltage on the primary side, and your primary side, by the way, for this donut is the conductors themselves. It's just a regular transformer with a primary and secondary, but it's a special design. The primary is actually the conductors going through the window of the CT or the donut. So if there is any magnetic field, residual magnetic field or difference between currents going in and out, this magnetic field would induce some voltage on the secondary circuit of the current transformer, and this voltage is proportional to the difference in the two currents, the difference in the current, which would be proportional to the leakage current. And this would trigger the electronics in your device, the solid state circuitry in the chart shown here. And based on the design, it could trip right away, or of course the device would analyze the difference, whether it's more than the 6 milliamp, like the trip level, or not. It's more than the threshold, then the device trips. And then if there is a curve built in, like the green UL curve that we showed in the previous slide, then it would start determining after what time it needs to trip based on the amount of current measured as leakage, or if there's no curve in the device, it's just designed to trip instantaneously, then it would just trip right away. And this is all the solid circuitry. The electronics would do this for you.
Right. And then this shows how this is your 3-phase GFCI, how that would work. And again, this current transformer has to encompass all of the conductors. So any current that in this case goes outside the path through the individual. It doesn't matter. It doesn't have to be a person. It could be a piece of equipment. It could be a shovel. It can be a screwdriver. Whatever it is that causes the current to go outside of the path. And it could go over this equipment grounding conductor because of a fault internally, and there's nobody involved. But in a three-phase circuit, all of your currents are sort of cycling back and forth, and you're balanced your type of load. And even if there's a neutral involved, your neutral would have to come through that CT as well. So it's just looking at the balance of current. And I've had questions before where they'll say, I have a knob and tube wiring. Can I use a GFCI circuit breaker or a GFCI receptacle? And the answer is yes, right? The key thing is, how do you get power to the controls? So if you look at a typical GFCI breaker, you'll notice there's a pigtail on the end. And the reason that's there is because you take your hot or your neutral. Say this is a shared neutral, and you have your hot and neutral on here. But if it's a single pole, you would, again, this is a hot here and a neutral here. Your other hot goes here. The neutral goes through this CT that's inside the system, inside that unit, and then it connects to the neutral bus inside the panel board to complete the circuit. Now, it's very important that this pigtail be connected, because that's how the brain, which is that control circuit, the electronics inside this device, get powered. If you don't connect that pigtail, you basically have a very expensive thermomagnetic circuit breaker, okay? Because that brain needs to be powered and energized. The receptacle gets its power from hot and neutral that's supplying this device. So it does not necessarily need an equipment grounding conductor. When I'm looking downstream, I can have my hot, as long as I have a hot and a neutral. Or if I just have two hots. I get that question for like pool pumps. They'll say, well, I'm only taking two hots. What do I do with my GFCI breaker? I don't have a neutral to land on there. That's perfectly fine. You still have to land this pigtail, but any current that goes outside of that path, as long as it exceeds that threshold, this device is going to take it off. So that's basically how it works. I have a couple diagrams to help you understand and see that pictorially. Again, I'm showing the CT. I'm showing the hot and your ungrounded and your grounded conductor. If I have a very large lamp drawing 5 whole amps, I think Don Gannier pointed out, I used this once before, and he was like, man, that's a big lamp. Yes, it is. But if my current goes outside of the path, at least 0.007 or 7 milliamps, it exceeds that threshold, it'll open. My your load that might be maybe a pool pump or some other. This would be I have 2 ungrounded and 1 grounded conductor going out to a load. I could go to a load that doesn't have the grounded conductor. Just 2 ungrounded conductors supplying that load, whatever. Those conductors go through that current transformer. Anything goes outside the path, I trip. Now, it's important to remember that a GFCI doesn't protect from all shocks, right? If, in this case, we take a guy by the name of Joe, and he takes a hold of the hot and the neutral, he becomes a load on the circuit, because current is not going outside of the path. It's just flowing through Joe. Joe is a load on the circuit. This current transformer sees current going out the hot and coming back the neutral. They will sum up to 0. Joe is just basically a part of the circuit now, and it's unfortunately the normal path of the circuit, and Joe is involved with it. So grabbing hot and neutral will directly put current through the body. Yes?
Yeah, Tom, this is a great point, because it emphasizes, or this slide is great because it emphasizes that GFCIs only work on differential current. It works on the difference. What the difference of the current is what triggers a GFCI. You can have, like Joe could be having 100 amps going through his body, but the GFCI would not see it, because what is going in one direction is returning to the current transformer. So from a GFCI perspective, there is no difference. There's no differential current, no leakage. So it's not going to operate. It's not what it's designed for.
Yes. And if you think about it, that's how a lot of the test units, when we have these GFCI testers or indicators, when you plug it in, what it will do is it generates current and sends it over the equipment grounding conductor. So if I have a knob and tube wiring and I don't have an equipment grounding conductor, my tester can't bypass the circuit, so I would not be able to utilize a tester on that circuit because I can't send the current outside of the path of the hot and the neutral because there is no equipment grounding conductor. So if you don't have an equipment grounding conductor connected, that presents a challenge from an indicator or whatnot plugging it in. But the only true way to test any of these products, whether it be a GFCI receptacle or a circuit breaker, is to test that button on the face of the device. You do that at first installation, and you're supposed to do that on a monthly basis. In fact, when I took out the in our circuit breaker, I take out the instructions for the circuit breaker, which you know where these end up, Nihad? They end up in the dumpster, right?
Of course.
But what was interesting was, I knew that we put in labels that says, circuit breaker GFCI protected, where you could put this on your receptacle that might not be a GFCI receptacle, or you could put this on a load to say that it is protected by a GFCI circuit breaker, so you know what is and isn't. They also have a sticker in here that says test the GFCI at least once a month, push the test button, and it gives you instructions on how to do that. And there's another label in here that says this device does not guard against electrical shock hazard resulting from contact with any two circuit conductors. So they have a test record and a test reminder that you can put a check mark every month. You could, if you have a circuit breaker, you put this inside your panel board, and this could be your record of maintenance on your GFCI. So you can check these off every month, and you can do it in, every year annually. We have certain time, like we'll run off the time change to check our batteries in our smoke detectors, etc. You can, establish a cadence inside your home with regard to your GFCIs to say, test these, and always test before use, especially if you're using a GFCI receptacle. You can press this button every time you plug something into it. Press the button and reset the button. That's the value of a local resettable device at point of use, which is, again, this might not be at your point of use. It could be anywhere in the circuit, which is a challenge. But in any case, I have to say we should be reminded that we need to test these devices monthly.
Tom, you're bringing a very good point there, because absolutely you have to test the device. And how many of us go to like travel? And of course, I miss traveling. We can't travel anymore, but hopefully we'll be back soon. But how many of us would travel, check into a hotel room, and test their GFCIs in your bathroom? I don't do it myself. I just don't avoid using the receptacle altogether, but it should be tested. But the point I wanted to make is the new UL standard, and it's not quite new anymore. It came into effect in July 2015, required that GFCIs have a feature, and this applies to receptacles and breakers, have a feature called self-test and power denial, which means that the electronics, it's more like you think of it as a watchdog in a code. The device is constantly testing itself, and it would interrupt power or give you some indication, whether visual indication or audio indication, that there is a problem in the device itself if there is a failure in the electronics. So this was all driven by the fact that most people don't test GFCIs in the field. I believe it was an EMA research, CPSC, Consumer Product Safety Committee, and both of them, I guess they found some like north of 60% of installed GFCIs are malfunctioning. They're not working. They're just sitting there. You have this veneer perception of veneer of safety that you are protected by GFCI, but actually the device failed because different reasons, and it's not working. And of course, like Tom said, the user is required to test once a month regularly, but because people most likely don't test it, so now GFCIs test themselves and let you know if there's a problem. The only problem in this test is if you're testing the self-test and power denial, it's testing the electronics of the device, but it doesn't test the interrupting mechanism, like the contacts of the device. So if, let's say, you have a welded contacts, you won't be able to catch this because you only test the electronics. The only way to know that everything is working as it should is by pressing this fancy test button on a breaker or a receptacle, because this way you're injecting an extra current uh, into the hot, and it goes to ground. It's not returning to the neutral anymore, which would trigger the GFCI to trip, whether it's a breaker or a receptacle. But like I said, the self-test is a step forward, but it tests the electronics, everything internally, but it cannot test the the interrupting or the breaking, the context, the mechanism that actually interrupts power.
Yep. And we're moving into GFCI solutions, and I was just looking at a discussion on the YouTube, a question Lisa Koyen asked about are you no, not Lisa, but it was I think it was Ahmed asked why the 30 milliamp breaker in North America are only specified for equipment protection if it's just the deals with time. And the reason is because the UL 1053 standard does not limit the amount of time. It's very flexible in the amount of time that you give these 1053 type of devices, which are your ground fault protection of equipment devices, to clear a fault for equipment level protection. They don't respond in that 15 millisecond time period based upon the curve that we looked at earlier. You can, for some current values, like up to 110 or 115% of their threshold, they will they'll give you like up to 2 seconds. So it's really important to understand that the UL 1053 device is not people protection, and it has to do with the clearing times.
Tom, for this, it's a good question, and Ahmed is another buddy from Saskatoon, so there's two of us from Saskatoon on the podcast here. Yeah, I know he's my friend, so hi, Ahmed. But to answer his question, it would be very clear in one of the coming up slides. But for now, it's just the difference in like I said before, like a fundamental difference between personal protection in North America versus the U.S. North America, versus the Europe. In North America, we decided that we are providing let-go protection as well as ventricular fibrillation protection. So the 30 milliamp does not provide the let-go protection. That's why those breakers are listed as ground fault equipment protection, although they could have the same tripping time as the Class A GFCI, but they're not operating between between 5 milliamp to 30 milliamp. They don't operate in this region, which is the let-go protection. That's why they are not listed or allowed to be used for personal protection. In Europe, they are used for personal protection, again, because of the fundamental difference. And this would be a good segue when we get to discuss special purpose GFCIs, the higher classes of GFCIs that allow up to 20 milliamp of leakage. But I'm going to wait here, and this will be clear when we get there.
So, and I think this is the table that you're talking about, right, Nihad? Is this? Yeah. Why don't you walk us through this real quick?
Okay. So, I guess just to clarify a few things, if you're not familiar with GFCIs, the standard GFCI that we use is actually called Class A GFCI. It's not just GFCI because there are other classes of GFCIs. The popular one is Class A, and because it's the most popular one, we kind of dropped Class A, so people say GFCIs. There are Class C, D, and E, and all of them altogether are called special purpose GFCIs. UL terminology is kind of tricky because special purpose doesn't mean that they are used for special applications. They can be used. I will explain the difference, but they can be used in any application that Class A can be used under those conditions in the chart. So there doesn't mean that they're special purpose, like they have some special application. They can be used in any application a Class A can be used. And to back up, all those GFCIs are required to be, like Tom said, you don't require an equipment grounding conductor for the GFCI to operate, but it must be, like GFCIs are designed to work on a grounded system, a solidly grounded system, or even high resistance, but mainly solidly grounded systems. If you have an ungrounded system, GFCIs are not going to do anything. It's like the Joe example, the slide that had Joe. If you don't have a path to ground for the leakage, the GFCI is not going to work. So GFCIs are only designed to work for grounded systems. Class A GFCI, from a standard perspective, it's UL 943. 943 is a harmonized tri-national standard, which means it's the same standard in Canada, US, and Mexico. C, D, and E are different. They're special purpose GFCI. The standard is UL 943C. C has nothing to do with the class. It's just C because there's a UL 943B, which covers something called ALCI, equipment leakage circuit interrupters. Equipment leakage circuit interrupters are those devices that you have in a, it's like a listed component, GFCI, not GFCI, it's like a, it's used in, hair dryers and the, mainly hair dryers and equipment that you kind of into the plug. It just like it's more of a GFCI in the plug of those devices in case it's plugged into a receptacle that doesn't have GFCI protection. So this is UL 943B, which is appliance leakage circuit interrupter, ALCI. And then when they had this no standard for the no classes C, D, and E, they said, okay, let's have UL 943C to be the standard that covers those GFCI class C, D, and E. UL 943C is not harmonized, which means it's only a UL standard. Like Canada and Mexico, they don't have those kind of classes defined in those countries. The C, D, and E classes are only in the US for now. Someone would kind of notice, where's Class B? If you're thinking, where's Class B? Class B is actually obsolete because it was those, Class B was actually used in light, swimming pool light fixtures before the adoption of the 1965 NEC. So prior to 1965 NEC, you could have what they called a Class B, and it was dedicated for light fixtures in swimming pools. Doesn't exist anymore, so Class B is obsolete, which kind of explains the gap A, C, D, and E. And so if you look at the difference, this kind of quick chart, this chart is based on a chart coming adopted from UL 943C, which is the special purpose GFCI standard. The misconception is some people would think, okay, the Class C, D, and E are more industrial because of the higher voltage, so they require higher amperage, which is not true. The difference between the classes of GFCIs is actually the voltage to ground, not the current. Class A, they're not popular, but you can find a Class A GFCI listed, Class A GFCI up to 100 amperes, which in the UL standard or CSA Mexico, there's no limit on the current, load current of the Class A GFCI. The limitation is the voltage. So Class A is only applicable up to 240 volts, which is equivalent to 150 volt line to ground. So if you look at this chart, if your voltage is less than 150 line to ground, and this is the 120, 240 volt line to ground systems, which is residential systems, you have a Class A GFCI. But if your voltage is over 150 volt line to ground, I'm talking about line to ground, we have a decision to make. If your voltage to ground is higher than 300 volts, which means, if you think of it, this is the 480 volt versus 600 volt. And this is the main distinction between Class A, C, D, and E. Class A is up to 240 volt, C, D, and E can go up to 600. But if your voltage is less than 300 volts to ground, you get a Class C. And this is typically what is used in the US, the 480 volt systems, because 480 volt, what's your voltage line to ground? 277, right? So 277 is under the 300 volts, so you get to Class C GFCI. But if you are over line to ground 300 volts, this is the case for what 600 volt systems. Your line to ground in this case is 347 volts. So now you get into Class D and E. It's mainly more 600 volt systems are not very popular in the US, so I would say Class C is the main class in US, but D and E are in those cases when you have 600 volt systems. So there are two distinctions. What, like this big box that says oversight the equipment ground, and what does this mean? UL wants to limit the voltage to ground, which is the voltage across the equipment grounding conductor. And if you think of it, if someone comes in touch with a faulty equipment, the voltage across the equipment grounding conductor is the same voltage across the person touching this equipment. So they want to limit, in other words, limit the touch potential to 150 volts. And if you can do this, then you have to oversize your equipment grounding conductor, which is very hard to be able to use a Class D. Very difficult because you have to go, and in the UL 943 standard, there is an Appendix A, I believe, Appendix A, and it gives you the equation on what you have to do to oversize your equipment grounding conductor to meet this 150 volt to ground limitation. If you can do this, again, because this is not a manufacturer controlled parameter, this depends on the plant and the design, and it's really almost impossible that you get someone to go in a facility and change their grounding to oversize all the equipment grounding conductors so that the voltage is limited to 150 volt to ground. So if you can do this, then you switch to class E, and class E is extra, like ultra fast kind of GFCI that it trips really, really quickly. And if we go, I think, to believe the next slide would show the difference between those classes, like the class E that trips really quickly, or maybe it's a couple classes down, but class E is just like really quick trip level trip performance that you have to resort to using class E if in the case that you can't oversize your equipment grounding conductor to be able to use class D. Again, both these classes are used on 600 volt systems mainly. If you're using 480 volt, which, like I said, the main system used in the US, Canada uses more 600, then you can use class C.
Yeah. Now, it's important to note that the code, the National Electrical Code, when it says GFCI is required, it only means a Class A device. So all of those other class devices are not necessarily permitted for use when it says you have to have a GFCI. So that's a very important piece of the pie. Just looking at, I'm sorry?
Special purpose.
Yep,
and all of them, their trip level, remember we said class A is between 4 to 6. For special purpose, it's 15 to 20. So we always say 20 milliamp, but it's the range of tripping is between 15 to 20.
Yep. So if you look at how these GFCIs are constructed, you have, like, from a receptacle perspective, there's a lot of stuff that's in here. You've got your contacts, your face contacts, so we're going to have a set of contacts in here. You're going to have terminations, terminals, and then you're going to have a printed circuit board, which is where the brain is that does all of the work in determining what's going on. And this is basically inside of a GFCI and how it functions. You have current going out the hot. So this is a GFCI receptacle. So you'll notice that I have where I come out the face, where I plug in, but also feeding downstream, so I can supply other standard receptacles downstream or a load of some sort, and still get GFCI protection because the current transformer is before that separation happens. And then when current comes back, as long as everything goes out, is coming back, then I won't trip. If I look inside of a circuit breaker, there's the pictorial, or there's the actual CT. You'll notice in here that I have my hot conductor, my ungrounded conductor comes in here, and it feeds down through the CT. My neutral lands here, it goes through the CT, and then passes up through the system and comes back, and your neutral comes through, and so there's your grounded conductor comes in on this terminal here, and it comes right back out again into the pigtail. So it makes sure that current goes through that sensor so that we account for all of the current going out and coming back. And the way a circuit breaker circuitry looks, you have your current that basically goes out to the load and it comes back through the pigtail, and that's that loop. Now, when you press the test button on a circuit breaker, what that does is it takes that current through a different path. So it comes through the push button, around the CT. So I have current going through the CT, but not coming back through the CT. So the push to test button reroutes it through the equipment grounding conductor or around that CT. And the same thing happens when you push a button in the receptacle. It sends it around through the equipment grounding conductor. And then you have your portable use, the same type of electronics and the same methodology. There's a CT right here where all of those conductors pass through. Everything has to be accounted for in the circuit. And this is your ground fault plug-in for your portable. It's the same deal. You can use a GFCI on knob and tube. There's not a problem with that because you just have a hot and a neutral. Any current that goes out of that path of the hot and the neutral, or your ungrounded and your grounded conductor, then it'll trip. So yes, you can use it on knob and tube. Okay, we're getting close to time. I'm going to go through some of this pretty fast on the performance criteria, Nihad. We'll glance over it, and then I'm going to get to the quiz questions from the Mentimeter. So we grouped, Nihad and I grouped the tests into three areas. You have a performance test, you have a withstand test, and environmental tests. And if you look at the UL standard is 943. When you look at all of the different performance tests and withstand tests and environmental tests, you have the performance has to not trip on leakage current, has to not trip or on recognize high resistance ground faults, open neutral situations. You have your trip thresholds in your time. You have your grounded neutrals we have to be able to detect. Withstand, these are your impact, your drop tests, your voltage surge tests. Any of the temperature tests and things of that nature, surge currents, any abnormal over voltages and things of that nature. And then you have environmental, you have your humidity, your temperatures, any corrosion and things of that nature, spill. So, the 943 type of device, whether it's a receptacle or not, it goes through a lot of tests. And then this is, a supply side open neutral for the portable GFCI. So some devices, some GFCI devices will have to go through extra tests because of how they are used and employed in the field. A receptacle has to go through certain tests that a circuit breaker doesn't necessarily have to go to because of its location. A portable GFCI has to go through certain tests because of its location in the circuit. If I have a portable GFCI on an extension cord and I, for some reason, break my neutral, my grounded conductor, I need to be able to detect that and still provide protection to this individual.
And Tom, and the reason is, and it's very similar to what you mentioned with the pigtail. If your neutral is open for whatever reason, let's say a broken conductor or a loose connection, then the GFCI is not powered. Like the electronics is not powered. So you have a GFCI sitting there and not doing anything, and you can have a fault like this stick man with the path. Like if you cannot see the current going between the path A, B, C, D, and back to the source. So this person is getting a shock, but the GFCI won't detect it because the electronics is not powered. So it's very important, and it's only required for portable because permanently connected GFCI, the assumption is they are installed by the qualified electrician, someone that wired, like Tom mentioned, the pigtail for the breaker. So you don't need to do this on a permanently connected device. It's only for portable GFCIs, like a power cord or like a power bar or something. Those kind of devices, GFCI portable device.
Yeah, and then you have your grounded neutral. So if I have if my system gets grounded somewhere before that GFCI, I also have to be able to detect that and still provide protection going through sticky guy, right?
Yeah, sticky guy, very sticky.
Yeah, and then this is that GFCI protection zone, which we already covered. We have the 4 to 6 milliamp, that Class A device, and then you have your Class C and D device. That's the performance chart that you were talking about, Nihad, earlier.
Yeah, and Class A is not shown on this chart because when you get to 300 milliamp, and instead of having a fixed 20 milliamp, fixed 20 millisecond response, the Class C would transition to a quicker inverse curve, a different equation. So they don't share the same curve. And this is kind of the chart I mentioned when answering the question that Ahmed had with regards to the 30 milliamp. Class A, C, D, they all have the same response, but Class C and D, they start later. They start at 20 milliamp for the tripping. So anything less than 20 milliamp, they are not providing any protection. They don't see this because it's less than the threshold. But when you go to the right of the 20 milliamp, they both have the same performance. I mean, as per UL, depends on the manufacturing design, but this is the limits that let's say at 50 milliamp or 100 milliamp, a Class C, D, or E should have the same time response.
Yep.
And then
and if we look at the National Electrical Code and how it's progressed over the years, GFCI protection first hit that book in 1968 for swimming pools and underwater lighting for the obvious reasons. Probably they had people who were killed in swimming pools because of the shock and leakage currents and things of that nature. And it expanded to bathrooms and temporary wiring receptacles, then garages. And in fact, in those early years, the equipment grounding conductor, 3-prong receptacles took a journey in the NEC where you had two-prong receptacles that were permitted, and then they added that you had to have the equipment grounding conductor connected to certain areas within a residential home, and eventually you can't buy receptacles for a new installation that's not got the equipment grounding conductor prong in there. And so as you look at expansion in the National Electrical Code from the 90s to 93, we've had seen continued expansion even up and through the 2020 code, where we've expanded even more to outside circuits. We removed the 15 to 20 amp limitation for residential in those locations. We moved other than dwelling units to 50 amps and 100 amp circuits, three-phase. And the Canadian code, electrical code, took a similar journey with regard to expansion from the early 70s all the way up to today, and they continued that expansion, which leads to a lot of the success of the GFCIs. We're seeing a downward trend in electrical from the Electrical Safety Foundation International .org. ESFI.org has a lot of statistics on this, and we're showing that shocks are going down considerably. And I always say in that regard, it's GFCIs is one piece of the pie. A lot of other things changed in our industry that are causing these trends to go down. We no longer have metal tools. We have insulated handles. We have double insulated tools. We have insulated appliances we use in our kitchens. There's a lot of things. We're all educated. There's a lot of things that have occurred that it's not just the GFCI that's causing the downward trends of electrocutions, which is an important thing to remember from a holistic perspective in that regard.
Team effort between GFCIs, double insulated tools, and better wiring methods. We have much better wiring methods these days than back in the day, and all of them are working together to make us safer and just minimize lower the shock incidents.
Yes,
it's a teamwork.
Absolutely. Absolutely, Nihad. Okay, so what I'm going to do now is I'm going to walk through the quiz, and I had some questions in the initial Menti code, which I didn't mean to put it in the middle in the initial one. I was just going to put it at the end, but people answered them. So we had 35 respondents on this one, and that means that we've got 35 people that have their name in the hat for the ShockWeek mug, which is a good thing so far. So the maximum threshold for a GFCI is indeed 22 or 6 milliamps, which we had 22 correct respondents. I put the 4, 5, and 6. The upper threshold, to Nihad's point, 5 plus or minus 1 milliamp is the way that we operate in this in that world from a receptacle or from a GFCI perspective. The UL standard for GFCI products is UL 943. UL 489 is for circuit breakers. UL 1699 is AFCIs. UL 1053 is ground fault protection of equipment. So we had 15 people get UL 943, 14 out there who were very honest, who did not know. That's why we're doing this program. UL 943 is your reference for the GFCI standard. All right. The next question was, or is, which is an outlet? Option 1, we had 7 people say that a receptacle is an outlet. We had 12 people say option 2, which is that box is an outlet. And then 17 people say that option 3, which is the receptacle with a face cover as the outlet. And it's important to understand this for the reason, the GFCI requirements in the National Electrical Code will say receptacle or receptacle outlets. In some cases, we say a lighting outlet. In some cases, we say all outlets need to be GFCI protected. So the outlet in this picture, the outlet in this picture is actually option 2. That is your outlet. It's not the receptacle. The receptacle is a receptacle. The receptacle with a cover plate is a receptacle. So it's important to understand what a receptacle is, what a receptacle outlet is, and what just an outlet is, because that will determine, in some cases, whether or not you have to GFCI protect that circuit.
Yeah, it's kind of confusing, Tom, the terminology in NEC. I don't know if you agree with me, but yeah, because we say receptacle outlets, so it gets confusing. I was confused when I first joined panel 2. It's like, what's an outlet? What's in the receptacle? But yeah, it's a bit confusing.
Oh, I agree 100%. And you know, the code is trying to clarify that, make that easier to understand more and more. But so what's the maximum threshold for a UL 1053 device? That is ground fault protection of equipment, which we talked about. We had a lot of people say 30 milliamps. We had none of these. We have an I don't know. And the right answer is none of those, because the threshold for a UL 1053 device from an ampere perspective is defined by the manufacturer, or it's defined by the person who sets the ground fault protection of equipment device.
Yeah, 1053 doesn't have a trip limit. It's usually they define it in terms of a percentage of the pickup current. So if your pickup value is so and so, then at 85% of that value, you're not supposed to trip. At 100%, you trip. I think at eventually, like there's no specific time, and 150%, I think you trip in 1 second. I can't remember the exact details, but they define the trip time based on the percentage of your current pickup value. And like Tom said, the pickup value is determined by the manufacturer or usually by the user who sets the trip point. If you notice, a ground fault relay or any 1053 device would have a set point to determine your current. GFCIs don't. GFCIs have a fixed trip level. It's 6, 5 plus 1 minus 1 for class A. They have 20 milliamp. You can't change the time setting nor the pickup current. But for 1053 devices, ground fault relays, you usually can set both the time and the pickup value on those devices.
All right, so we're over time here, so I'm going to try to get through these last questions. What is the let-go threshold for a healthy male? Now, we said 30 milliamps, but in reality, we showed that chart. It's probably up there around 50 milliamps, but from a European standard perspective, they set that threshold at 30 milliamps because they protect from a threshold. So that's sort of the number. I don't know, Nihad, if you agree with that one or if you think it really should be around 50 milliamps. What are your thoughts on that? Do you agree with the answer to this one being 30 milliamps?
Are you talking about let go threshold or ventricular fibrillation? I think this should say ventricular fibrillation, right?
Let go threshold. Is that 5 milliamps for let go threshold?
It's like usually use 10 to 15. Yeah, like I would say 15 will be the max. Like it's like 8 to 10, or sorry, 8 to 15 usually the range. So 10 is kind of in the chart that we showed was 10. So yeah, I thought that the title you talk about ventricular fibrillation because
you're probably right. I got to restate this question.
Yeah, they don't do let go threshold, let go protection in Europe. So 30 milliamp is too high. Like you can definitely won't be able to let go at 30 milliamp. There's no way.
Okay, so this one is a GFCI is your first level of defense against shock. True or false? 19 people said true. 17 people said false. Nobody didn't know the answer, and I would say that the GFCI is your last defense against shock. There are a lot of things you should be doing first. If you relied on a GFCI to give you protection, then something went wrong, and we're going to talk about that with Jim Dollard on Thursday, so you're going to want to stay tuned for that discussion. But the answer to this one is false.
Thomas, the GFCI, just for everyone here, it's simply your airbag or the seat belt.
Right.
You have to kind of make sure that you follow the rules, drive carefully, defensive driving, whatever. But it's there when something bad happens. It's not there to protect you. Like you can just rely on GFCI. It's your airbag in your vehicle or seat belt.
Yep.
That's how I call it.
And GFCIs require an equipment grounding conductor to operate properly, and the answer to that is false. We already talked about that. I could work this on shared neutral. I can work this on knob and tube, etc., or just without an equipment grounding conductor. So I do not need an equipment grounding conductor to operate properly. You cannot put a GFCI receptacle downstream of a GFCI breaker because they will have tripping issues. And the right answer to that is false. And most of you got that right. 26 of you are right. That is false. You could do that. I don't know why you would, but that will not cause nuisance tripping issues. And you can put a GFCI receptacle downstream of an AFCI circuit breaker. There's no problem with that. So the right answer to this is also false, which the majority of you got that correct as well. You no longer have to test GFCIs because the standard now includes self-test requirements, and you covered this, Nihad. The answer to this is false because you can't test, the self-test can't determine whether or not there's welded contacts or mechanical nature type of issues inside. So the answer to this one is false.
Only testing electronics. Yeah.
All right. So we went through the questions. And what I'm going to do now, Nihad, is I am going to go and we've exceeded our presence here on this topic. We've gone through pretty much everything. There was only a couple slides that I skipped over, which is not a big deal. Talking about a little bit about the future and whatnot. But the Menti code, for those of you who completed at the beginning, the Menti code's displayed down below. Take a look at that down below. It is 410452. The questions that are on there are the exactly same ones that we just went through. I appreciate anybody who's going for that. That'll give you the PDH certificates, and what that will do is get you a chance to win the official ShockWeek mug. And I'll tell you what, this is serial number 1. I'm going to put that on the bottom. I'm going to start numbering them, Nihad. I'm going to use a magic marker, and I'm going to number them. They're going to be special mugs.
Tom, and you get a shock too. We agreed that to get a mug, you have to get a shock, right?
No. We don't want to do that. Don't want to do that. You don't want to get a shock. Nope.
Only Jim though. Okay, we're only shocking Jim.
Yeah. I'll have to work those details out with Jimmy. But in any case, I hope everybody got got something out of this program. I'm going to take a look, Nihad, as they're doing this log out. I'm going to take a look online to see what kind of questions came in on YouTube.
Yeah, I mean, we had a couple slides left in the future, but I guess, we're running out of time, so it would have been kind of...
Oh, Don Ganir pointed. He picked the box as an outlet, but he wasn't sure because there weren't any wires in there, and it's not really an outlet unless you have wires in it. And he's probably right. I should change that picture, Don. But good point. It's not an outlet unless you have conductors that you have to wire to. It's just sitting on the shelf in the box. It's not an outlet yet until you install it. It's just a box. I like it. So John Clements asked about insight on 210.8A10. Nihad, we expanded. If I look at the code book in 210.8, as people log off and all this other good stuff, we moved and expanded the GFCI requirements in dwelling units. We moved up to all branch circuits, any rating in those areas. So we still kept those rooms. We expanded in basements, not just unfinished basements. But if you look at in 210.8F, it says outdoor outlets, which is completely new. All outdoor outlets for dwellings other than those covered in 210.8A3 exceptions supplied by a single phase branch circuit rated 150 volts to ground or less, 50 amps or less, shall have ground fault circuit protection for personnel. So not only did we expand to any ampere rated circuit in any of the areas that are listed in there, which would pick up in a say one of those, what do you call it, the laundry. We picked up the dryers in the laundry. Because we have the basement, we'll pick up any electric water heaters and things of that nature, right? Outside circuits, we picked up an outlet, but so in A, we expanded to any of those, but it has to be a receptacle outlet. So your water heater would have to be a pluggable water heater, right? But if it's an outside circuit, we said all outdoor outlets for dwellings. That gets you to your hardwired equipment and whatnot.
210.8F.
Yes.
New section. This
Yeah.
was my public. Remember, that's my proposal. It's causing a lot of issues these days. I'm shocked, but yeah, there's a lot of problems happening in the background.
Yep, and that was your public input, because I remember you sending me that case. You sent me an email with a link to the case of the boy who jumped over the fence and grabbed that air conditioning handling unit.
Yeah, it was in Chicago. It's a very sad incident, but I guess the air conditioning wasn't wired properly, and this poor kid was playing with his buddy, and he wanted to jump from, like, his neighbor jumped over the fence, and he grabbed the fence, landed on the air conditioning, and boom, there was potential difference between the ground and the air conditioning. was
Yep.
shocked.
You were shocked? Yeah, it's amazing how different
The kid was shocked, and he just got.
Yep. Yeah, you were breaking up there, Nihad. Your video is a little. I think it's because my system is probably giving me a hard time. But
So yeah.
yep. So we had Susan Newman Scarcey on Facebook. We had Chris Fawcett on Facebook and a few others on YouTube. We're saying goodbye to everybody right at this point. So John Clements, I appreciate. Dawn Ganir, thanks for joining us again. Bhaskar Banerjee, please, thank you for joining us, and anybody else on YouTube. Hopefully you got something out of it. I appreciate you dialing in. It'll be up there and available later as well, so it'll be on my YouTube channel for your later viewing pleasure. Share it with others. Send the link around, and hopefully the information that we covered today was of use to you and gives you some background and understanding of not only the standard, but where some of these limitations, these threshold values came from a historical perspective. And if there's anything that I can do for anybody out there, please feel free to reach out to me. And I know, Nihad, you probably say the same as well.
Yeah, and thanks everyone. I couldn't see the thank you, Tom, of course, for the invite and for everything. I couldn't see the chat, but now I'm looking since we're done, and I noticed a couple of friends like AJ and Ahmed. So hi everyone. I wasn't following the chat, and I noticed there's a question that where I was from. I said I was born in Cairo, Egypt. I don't know if the person who asked is still online. But yeah, this is kind of to answer the question because directed to me. But yeah, thank you, Tom. It was great, and I hope everyone just got some value out of their last 2 hours. And yeah, if like Tom said, if you need anything, Tom or myself can help, please reach out. I'm on LinkedIn. Tom has my email information. You can reach out on LinkedIn, and yeah, hopefully you make everyone safe. And if you have any ideas for the National Electric Code, please go ahead and submit them. Unfortunately, things doesn't get changed unless there is an accident, which is sad, but this is the truth of it. So if you come across any instance, just please come forward and to submit a PI so we can make the National Electric Code safer for everyone.
Excellent. Okay, well, so from the Technical Social Distancing Network, Eaton's version of that, and educational information, I'm going to say thank you, and I wish everybody out there a great rest of their day, and we will see you tomorrow for our Motor Control Center discussion with Matt Hussey to take part 2 of that. And remember, stay safe and healthy as usual. All right, I'm going to end the stream. I'm ending it out there on Facebook land. And I will be ending it on our YouTube land. So take care. Thank you. God bless. All that jazz. Take care. You can stay with me, Nihad.
I'm here.
Perfect. Okay.